July 18, 1956, at the Boeing Airplane Company's Renton plant, an era begins as the first KC-135 jet tanker, an airplane with swept-back wings and pod-mounted Pratt & Whitney engines, rolls off the assembly line. And another era ends with the production of the last of Boeing's piston engine airplanes, the KC-97 tanker, which have been produced at Renton for the past 7 years. For airplanes such as this B-52, the KC-135 provides a new answer to an old question. What is the range of today's heavy bombers? Less than 10 years ago, the answer would have been relatively simple, a matter of computing fuel capacity against fuel requirements at the specified speed and altitude. That answer won't do today, for in 1947, at the request of the Air Force, the Boeing Airplane Company began investigations of flight refueling methods. The system which was developed, dubbed the Flying Boom, soon reached a point of high utilization with the KC-97s, tankers which proved their versatility in refueling such diverse airplanes as F-84F jet fighters, RB-45C reconnaissance bombers, and the medium jet bomber, the B-47. A working success, the KC-97 was limited in refueling the B-47s, and the descent refueling technique was devised to overcome the performance differences. The heavy B-52 bomber flying at a high gross weight must reduce speed almost to the stall point in order to formate with a reciprocating engine tanker. The need then was apparent, a tanker capable of speeds and altitudes comparable to those of the receiver. Boeing introduced its answer, the Model 367-80, on July 15, 1954. This prototype tanker transport was the product of the company's advanced planning in anticipation of future needs. The capabilities of the Model 367-80 were reviewed by the Air Force, and a tanker version designated the KC-135A was ordered into production on September 1, 1954. Even while the Renton plant was completing its tooling and beginning production, the Boeing 367-80, as part of an Air Force program for system development and performance testing, took part in a series of dry boom tests in which there were no actual fuel transfers, but which demonstrated the practicability of jet tanker formating and contacts. Following boom maneuvers to test aerodynamic and stowage characteristics, a series of formating and dry boom contacts was completed, covering the altitude and speed ranges best suited to optimum B-52 operation. These tests checked formating and contact positions, receiver visibility and the effectiveness of pilot director lights, and by maximum azimuth disconnects demonstrated the ability of the nozzle to clear the receiver airplane. To date, more than 600 flight hours have been clocked on this prototype airplane, providing an opportunity for KC-135 systems and controls testing, including development of the landing gear, brakes, lateral control systems, and the automatic pilot. While the first KC-135 was entering the final assembly stage at Renton, a static test airplane was being transported part by part to the Seattle Flight Center for a series of static tests, some of which call for the fuselage to be pressurized to almost 13 pounds per square inch, at the same time that ultimate flight loads are applied to the entire airplane. These tests, which will continue well into 1957, are substantiating the general design calculations, determining the true strength of the structure to obtain the permissible weights and maximum payload capability of the airplane, and have already dictated some structural improvements for the production design. For hydrostatic testing, which will begin in 1957, a tank has been constructed to subject a complete fuselage section to hydrostatic tests to prove the ability of the aircraft to withstand repeated pressurization cycles and flight loads, and to show the fail-safe ability of the structure to contain fatigue cracks and localized damage without explosive destruction. Testing and preparation have continued concurrently with production of the KC-135, which, like other aircraft, represents the cumulative effort not only of the Boeing firm, but also of hundreds of subcontractors. For more than 44% of the airplane AMPR weight is subcontracted to manufacturers large and small across the nation, including Roar Aircraft, Riverside, California, manufacturers of the stabilizer and also of the power pod packages. In order to facilitate this latter production, Roar is establishing a plant in Auburn, Washington, a community close to the Renton plant. Other major subcontractors are Northrop Aviation of Hawthorne, California, producers of the outboard ailerons, outboard wing, and wingtips. The Twin Coach Company of Buffalo, New York, the most distant of the major subcontractors, manufacturers of the vertical fin and rudder. And the Ryan Aeronautical Company of San Diego, California, manufacturers of the aft body section and the aft mid-body section, the largest airplane part ever to be moved by rail, measuring 12 feet wide, 40 feet long, and reaching 17.5 feet at its highest point. Rolling into the unloading platform at the Renton plant, these parts symbolize the success of the subcontracting program. The keynote of the KC-135 program has been cooperative effort, with Boeing providing to the subcontractors special assist teams whenever a production problem has arisen. These parts flow into the assembly line, where they are joined to the prime contractor-produced parts. The subcontracting program has made it possible to keep a production schedule that would be difficult if Boeing were to attempt to make the entire airframe. Indicative of the production capabilities of the Renton plant, however, are the double banks of gigantic wing jigs, providing for 3 left-hand and 3 right-hand panels simultaneously, and the inboard wing jigs, which feature the largest cast aluminum end gates in the world, 20 feet high, 6 feet wide, and weighing before machining 4,900 pounds. Further evidences of production activity are seen in these huge milling machines, which are turning out the boom tubes, spar cords, and wing stiffeners, nacelle support forgings, and through a unique freezing system, the honeycomb sections of the ruddervator. Because of the nature of honeycomb material, it is frozen to ensure stability during the milling process. The use of the honeycomb material in the ruddervator in place of the conventional structure achieves a weight reduction of approximately 75 pounds. The steady buildup of new jigs reflects the expanding production capability which is geared to a buildup to turn out 20 airplanes a month by July 1958. The airplane being produced at Renton has a wingspan of 130 feet 11 inches, a body length of 128 feet 10 inches, measures 38 feet 5 inches high over the fin, and has a main deck with a plywood covering 86 feet 8 inches long with a nearly constant width of 10 feet 9 inches and a ceiling height of nearly 7.5 feet. The main deck has provisions for either 45,000 pounds of cargo or 80 passengers. Under this main deck, adding to the fuel carried in the integral wing tanks, are the bladder tanks in the wing center section and the main body tanks. The body tanks are located fore and aft of the wing. Except for a 1,000-gallon reserve in the wing tanks, all fuel in the tanks at the time of contact may be used in flight refueling. This fuel is transferred through the boom, which has been modified from the configuration used on the KC-97 by refairing the boom and body boom combination and increasing the area of the ruddervator for increased stability and maneuverability. The boom operator in the KC-135 lies in a prone position on a platform facing aft toward a window, affording a view of the entire formating envelope. While the first KC-135 airplane was approaching the final stages of its completion with the hanging of the 4 Pratt & Whitney J57 engines, plans were continuing for the rollout and flight tests to follow, with pilot and crew members employing factory training units as a means of gaining a thorough knowledge of systems and operation. The training unit, which is set up to handle 14,500 man-hours of instruction per month, is equipped with devices simulating all the major systems components of the KC-135. supplemented by over 400 graphic aids transparencies. The first phase of the training of contractor personnel began in October 1954, and the majority of the personnel involved with the KC-135 have now received familiarization through the program, which operates as a continuing process, so that as changes are made in the airplane, the current configuration is taught. The initial group of Air Force testing, planning, and training personnel have also received familiarization through this program, which will continue for both flight and line personnel, for instructors at Air Force residence schools, and for members of the Air Force's Mobile Training Wing. Ahead of the first KC-135 on its rollout day lay a series of tests prior to flight. Before taxi tests, the airplane was checked to obtain data on surface hinge moments required to overcome friction. Lateral control is provided by an inboard and outboard aileron and 4 spoilers in each wing. Actuated through the 3,000-pound hydraulic system, the spoilers are positioned by the aileron control system for lateral control and may be operated separately for use as speed brakes. The outboard aileron is connected to the inboard aileron by a bus cable system and to the flap drive so that it will not actuate when the flaps are up, and will operate in conjunction with the inboard aileron when the double-slotted flaps are extended. Directional control is provided by a conventional fin and rudder positioned by a control tab in the rudder trailing edge, while movable elevators provide primary flight longitudinal control, and an adjustable stabilizer accomplishes longitudinal trim. Of the KC-135's 4 jet engines, number 4 is equipped with a self-contained combustion starter and compressed air storage bottle, making it possible to start the engines without employing an external starting source, supplying compressed air which is combined with JP4 from the airplane's fuel supply. Air pressure is bled from the bleed air manifold to start the other 3. For the test program, the KC-135 was instrumented with continuous dynamic recorders and photo recorders. Taxi tests at low and high speeds, begun on August 30, 1956, checked elevator and rudder operation, as well as spoiler and speed brake operation for response, with observations by the pilot of any time lag or possible erratic operation. On August 31, the first KC-135 was airborne for its initial flight, manned only by a pilot and co-pilot. Lasting 90 minutes, this first flight demonstrated airplane airworthiness and handling characteristics. In subsequent flights during Phase 1 testing of the KC-135, a series of tests was performed at an altitude of 10,000 feet to demonstrate the effect of flap and gear retraction on longitudinal control and longitudinal trim and control effectiveness. Lateral control effectiveness was also checked. At 15,000 feet, stall investigations were performed with stalling characteristics observed and records made of pitching, rolling, and yawing as stalls progressed, and further tests to determine the airplane's stalling speeds and flying qualities near the stall. Landings were checked to verify landing distances and characteristics, demonstrating the KC-135's tricycle landing gear system, including 2 main gears, each consisting of a 4-wheel truck and a steerable nose gear. The landing gear is actuated for normal braking by either the pilot's or co-pilot's rudder pedals. At the Boeing refueling ground rig boom tower, the airplane was subjected to additional tests, including a check of boom operation and fuel transfer system characteristics. General operational stability established, the next step in the testing program consisted of in-flight checks of the refueling boom to determine that the boom is stable throughout the range of normal operation, to check for the proper stick-free position of the boom, and to determine the control envelope and forces at a given airspeed and altitude. At high altitudes and speeds, boom stability investigations and flutter checks were conducted. With the boom extended 10 feet, studies were made of the control envelope, as well as the usual in-flight functional checks of the boom. The proof of the pudding of the KC-135 took place on October 3rd, 1956, when it participated with a B-52 receiver airplane in a series of refueling contacts. Operation of the refueling system in various modes was accomplished, with upper limit, lower limit, and right-hand azimuth limit disconnects. Disconnects were also made from the receiver pressure switch. Following these Phase 1 tests, this first KC-135 and the next 8 production aircraft will be subjected to further investigations, comprising an entire Air Force phase test program and directed toward proving the KC-135's operational suitability and capability. Tests conducted to date effectively demonstrated that jet-age flight refueling is a reality. The KC-135 and the B-52 can be flown at identical altitudes and speeds without penalty to the performance of either. Thus, the KC-135 will serve to erase limitations to B-52 range. The KC-135 jet tanker is a striking demonstration of the growth and development being poured into today's Air Force, providing a surer guarantee that American aviation will not be left behind in today's jet age.